But it's wonderful to see such a great crowd. I think most of you know I'm Mary O'Kane, the Chief Scientist and Engineer, and it's fantastic that we've now got our Science and Engineering breakfast here in Parliament House, because we can have wonderful ministers, and I'd like to welcome our Minister, Minister Roberts, and Minister Williams, who's the Minister for Aboriginal Affairs and Minister for Early Childhood. Welcome the members of Parliament who are here, that's another advantage of being here, and of course all our friends who come to these breakfasts. This is very much a exciting thing that feels like the future but actually is the present today. And I'm going to start with a trick question that I think I told you the answer to in a recent talk, and that is, which country has the most autonomous vehicles of all countries in the world? A little answer at once. The answer is Australia, and that's because of the automated mine in the Pilbara, the mine of the future with Rio. And today's speaker is the person who's very much responsible for that large number of automated cars and for a lot of the automated mining that happens in Australia. But today, Professor Salah Sukkarieh, who's the Professor of Robotics and Intelligent Systems at the University of Sydney, is going to talk to us about farms of the future, so how we use big robotics in farming. And I know some of you read about it in the Financial Review 2 days ago, and you can read about it, you can see great videos, but today's going to be a super talk. Salah's won a lot of awards and prizes. We were particularly proud that in 2014 he won the Science and Engineering, the award in Engineering and ICT of the New South Wales Science and Engineering Awards. Last year, as many of you associated with the Warren Centre know, he was the 2015 Innovation Lecturer, and there's loads more. So just before we welcome him, I do need to mention that Minister Roberts needs to leave at probably 8:15. You're not all to follow. He's the only one who's going at that point. It's not because he's not interested. I will be giving him a long version of the talk later. Ladies and gentlemen, please welcome Salah Sukkarieh.
Mary, thank you to all the team at the office as well. Thank you for your support and letting me present this seminar series. It's truly an honour. Ladies and gentlemen, distinguished guests, also thank you. I know it's taking up a lot of your valuable time. It's early in the morning, and hopefully this presentation will be informative. So what I will be talking about is, when you talk about farms of the future, in fact you talk about a lot of different things. It could be anything from glasshouses, commoditisation, genetics, so forth. There's many different aspects. But what I will be talking about is robotics and automation and data analytics, and how that's all coming together and transforming not only the industry but also the science, because for the first time we're collecting significant amounts of data 24/7, and that's going to change the way we think about crop models and animal models and so forth. So there's a play in both the industry and also in the science realm as well. There have always been farms of the future, that's always been around. This is a postcard from the 1900s in France, when they predicted what the year 2000 would look like. And a little farmer on the side there, pressing buttons and pulling levers, and everything else is automatised in some form out on the farm. But ever since we've been wanting to grow food for others, whether it's domestication of animals and how we use those animals on the farm, or it's mechanical tools, then it's mechanisation, and now we're leading into the realm of automation. And really why Australia is actually leading the world when it comes to the application of robotics on the farm is because, as Mary's mentioned before, we already have a large industry that knows about automation in different forms. There's the mining aspects that we have in this country, stevedoring, aerospace, security, infrastructure. There's a lot of different aspects around automation, and a lot of that technology cost has dropped, and now we're feeding it into the farming aspects as well. Ever since we started this work about 5 years ago, there's been a rapid increase in the amount of uptake from different growers and industry. And when reporters come along, they want to do two things. One is they want to take photos of all the robots because they think it's really cool. And then they go for the jugular and they tell you, are you really trying to put the grower out of a job? You know, is that your role? You know, are you trying to put the farmer out of their business? And in fact, this is more of a technology pull than it is a technology push. What we're finding is a lot of the industry and the growers want this technology because there's some significant constraints that they're going through. And I'm going to go through the first few slides. I'm just going to kind of highlight what those constraints are and how robotics is going to help that. This is a graph on the left that's showing you what the average age or median age of growers of different industries are, and the light blue shade that you have over here is the workforce. And one of the big problems that we're having, or what they say they're having, is that the median age of the grower is getting older. The average age of the grower is about 55, close to 60 now in Australia, and so because of that, there's a huge implication. The plot on the right is showing you what the average age of the grower is, the median age of the grower compared to CEOs and MDs, and the argument there is that, well, actually it's not that old, because compared to CEOs and MDs, we're pretty much on target. But what the growers will tell you is that compared to a CEO, the farmer is also the director for human resources, the director for maintenance and operations, the directors for research and innovation, etc., etc., etc. So they're doing a whole bunch of things, and there's no succession plan at the end of it all as well. So there's a huge issue that we've got there. This is using the Bureau of Statistics here, and you can see as the ag industry is diminishing in terms of labour force, we're finding what's available to growers in various forms. And then also, if you look at the labour market, this is the systems diagram of the labour market. It's a very complex beast, both in terms of local hire, the people on the farm, illegal immigrants, visas, etc. There's a whole bunch of play that works together. And then also, when you couple that with the wages as well, Australia has one of the highest wages in the world, if not the highest. We look at super and tax and so forth, then that has an implication. So to try and maintain international competitiveness when there's a labour market that's diminishing and the labour cost is quite high is problematic. And I like this plot because it gives me a relationship between land and labour productivity. If it's a log graph, so if you look at it, what it's trying to tell you is that if the curve is kind of going along the x-axis further and further, then we're improving labour productivity, but not land productivity. If you follow the dashed lines and what it says, for every improvement in labour productivity, there's an improvement in land productivity. And you can see in most developing countries, as you go, they're starting to curve off. If I pull out the Australia, New Zealand plot from here, they tell me from the Oceania, you'll also see that levelling off as well. So there's this relationship between how we improve labour productivity and land productivity. And the final thing that's really impacting the growers is this consolidation and market power that's happening. You're getting a lot of the big industry players that are teaming up with each other, working different ways, all the way from seed, all the way through to harvesting, and that's kind of pushing out the growers from the farm as well. And there's that impact about how technology is benefiting those big players and not benefiting the growers. And so a lot of that we have to deal with in terms of how we can improve the technology in that way, and dropping the cost. So we're not really trying to put these guys out of job. Like I said, it's more market pull, it's more technology pull from the growers than it is anything about pushes because of all these constraints that you have. There is another challenge that we've got, and that is the kind of team that you have to put together in order to make this work in various forms. And there's vet scientists, plant scientists, crop scientists, ag scientists, there's agronomists, there's the farmers, there's the computer scientists, the robotics engineers. All of these guys have to come together. We have to try and solve this technology and use this technology in some form. But just as importantly, there is no Rio Tinto, BHP, Qantas or anything like that, where there's one single entity that can come along and say, this is the 5-year, 10-year strategic plan for that particular industry and how automation comes through. And so what you have to do is you have to get your funding from different sources and then try and work out what that plan is, that technology that can actually operate across different types of commodities as well. And that's also another challenge that we have. So to kind of wrap up those first few slides and kind of get to the interesting bits now, really what I'm trying to say is that there's a significant drive for this type of technology to go onto the farm, to help the farmers in various forms because of all those constraints that I mentioned before, and they come with their challenges in terms of bringing in the science and the engineering. So the first example I want to look at is tree crop intelligence, and really what that means is, can I provide more information to the tree crop farmer about their tree crops, and in particular can I get down to the individual fruit or individual nut along in any part of their farm. And really where robotics kicks in here is the ability to be able to take sensors and position them anywhere on the farm repeatedly and with a level of accuracy such that we can look at change detection, for example, of an individual tree or individual crop as time goes on. To kind of give you some level of understanding of how we approach this, we generally go up to the grower and we ask them what their process is, and I don't expect you to kind of look through this, it's just kind of giving you an architecture that describes, in this particular case, how an apple grower goes through their season and what they do, and all the decision points that they make along that way. And there's various decisions that they have to look at as they're looking at their crop. And what we then do is, after we kind of look at that, we actually ask them for we actually go from this very structural form about how they grow apples down to another level, which is what we call the information form. And we kind of ask a series of questions. So this is showing you what they go through as time goes on around the season. And then we ask the growers a series of questions. So for each one of these aspects, what do they actually have to do? And they give us a list of all these tasks that they have to do. And then we go to each one of these tasks and we say, what level of information do you have about that particular task? And that little variable here, this little H symbol that you have there, is telling us that they have a high amount of information about that task. And then we also ask them, what impact does that task have on their productivity along the way? And so in this particular case, looking at last season's yield and quality, they have a lot of information about that, and it has a high impact on what decisions they're going to make this year in that way. The real critical areas are the ones that are in bold, because the ones that are in bold are where there's low information, but it has high impact on their decision making, okay, and high impact on their productivity. And it's those areas there that we target straight away, because that's where we can sit down and say, well, what we can do is we can provide high levels of information, and that will benefit you in terms of your productivity presentation. So you can see things such as a visual assessment of the flowering. So knowing the flowering will tell me a lot about pollination, will tell me a lot about my potential yield that will come through this season, as an example. And being able to do that is what's important. So over the last 4 years, we've had a program through Horticulture Australia about looking at different tree crop industries and how we might apply that. We built a robot. This robot, it's electric powered. One of the things that we aim for is looking at solar electric activity. So this is electric powered. It runs for about 4 or 5 hours. There's a collection of sensors on board, and these sensors are not the sensors that you would have on every farm or anything like that. What we did was we threw a lot of sensors onto the farm to kind of see what the information was that was coming back, and from that information trying to glean whether we can get any information back to the farmer. So you'll see there's a range of sensors. There's laser, there's camera data, there's radar data, infrared as well, there's thermal information. We'll try and look at, there's a natural gamma sensor here to look at ions in the soil. There's a conductivity sensor, so we can look at water properties in the soil. And what we're really doing is measuring what's going on in the ground and what's going on the tree simultaneously. And we're trying to do that up and down every single row as we go through. So what the robot's doing is it's going down these rows, and as it's going down these rows, this might be emitting certain signals, but it's also retrieving information as well, and we're trying to make sense of all that data in some form. Now, we could stop there, just collect data and then pass that data to a scientist, but as robotic engineers and so forth, what we'd like to do is be able to take that data and start to automate that processing as well. And so there are many different ways of being able to see a tree. In our minds, we can see these tree forms, and all we're saying here is that there's hyperspectral information, there's thermal information, there's laser information, so you can see some near infrared, thermal information, hyperspectral data and thermal data as well. And so there's different ways of seeing a tree, but to a robot, this is just just a collection of ones and zeros. Okay, that's all it is. And somehow we need to take all those data and we need to be able to apply it to certain types of algorithms, and from those algorithms be able to make sense of what goes on. And this algorithm structure that you see here is pretty much the essence of what we've done in almost all our projects. And just to kind of give you a bit of an understanding of what goes on here, there's this dotted line here which is representing up the top, which we'll call some training algorithms, and down the bottom which we'll call classification algorithms. The training algorithms are optimization algorithms, machine learning algorithms, and what we try and do is we collect large amounts of data. So the robot goes around, is collecting different amounts of data. We'll have to do certain things to the data, which is what we call image alignment, because we've got all these sensors positioned all over the place on the robot. We have to bring them to a common view and align all those images together. Once we have that, we can then start to feed it into some machine learning algorithms and optimization algorithms. And literally what that is that if I'm interested in apples, I will come along and pull out apples from each one of those images physically. I'll click on some images as a human operator, and I'll pass it to this algorithm, and this algorithm will look at things such as color and texture and shape and other spectral images, and it will try and learn the correlations between all that information. And I'll say, this is an apple, this is an apple, this is an apple. I'll keep doing that, and this algorithm will get better and better and better at learning what an apple is. And I'll take a flower, and I'll give it flower, and I'll give it flower, and say, this is not an apple, this is not an apple. So I'll give it the negative aspect, so it'll learn that that's not what I'm looking for. Likewise with the leaf and so forth. So you go through that whole process up here in terms of training up an algorithm. And once you're confident that the algorithm knows what an apple is, or what a flower is, and so forth, you can then feed that model into the robot. So now as the robot's going up and down the rows, it's collecting information, automatically aligning that data, and then determining whether or not it sees an apple or a flower or a branch or anything like that. And that's really what the architecture looks like. We're trying to detect individual features. So that's the first level of activity. So if we can come along and detect individual features, then we can add higher level algorithms on top. So we can look at crop yield information, crop forecasting information, integrated pest management. There's a whole series of algorithms in that we can write on top. So if I can detect individual apples, flowers, branches, leaves, trunks, whatever it might be, then I can come along from there, take that information, write higher level algorithm and say, this is what the flower count is in that particular row. In fact, this is what it looks like on that particular tree. In fact, this is how we segment it out. There's more flowers at the bottom of the tree than the top of the tree. Likewise with the apples and so forth. And that's what we do. So we send the robot out, it will go up and down these rows. The first challenge that we have is you can't just throw a TomTom unit on these things and tell it this is where the waypoints are if you go and follow through this or anything like that. The trees are high enough that you get attenuation of the GPS signals, so the robot gets lost if you just rely on GPS alone. So what it has is a collection of laser sensors and so forth, and it will look at the tree trunks, and it will use the tree trunks as guiding posts, and it will know where the tree trunks are, and it will kind of guide itself through the middle of all that. When you collect all the information, you get a lot of noisy data. So what you see here is these blue lines are representing the robot going up and down between the apple rows. Lots and lots of red clutter that's around there. So what we have to do is we have to start playing with that data and automatically segmenting out that data so that we get an image that looks like this. Now this is an image again, but what we're trying to do is just show you what the robot sees. The robot just sees a collection of ones and zeros, but what it's trying to do is it's trying to detect the face wall here of this whole apple orchard and separate it out from the ground and separate it from the rest of the sky. Okay, and being able to do something with that. It still looks like a wall, but that's a good thing. So even now, if I could just use that algorithm, I can start to come along and say, this is what the architecture of that particular row looks like today. A month later, the grower can say, go out again, what does the architecture of that wall look like again? And has it changed from the previous one? And we can do change detection algorithms that minus one image from another image and look at what the differences are. But what we want to do is go down to the individual level. So here we're looking at laser and vision data, and what we can do is detect the individual tree trunks. And once you've got the individual tree trunks, you can then come along and identify individual trees, okay, where the individual trees are as well. And so that messy data that I showed you before, that messy map data that I showed you before can be cleared up now, and now we know each individual tree and what each individual tree looks like, and we've got the individual face of that, what that wall is as well. And so back to this thing again, so what we've done now is you can collect all this information and say, okay, here's an individual tree, here's an individual tree, here's an individual tree, as the robot's going up and down, and then we've already trained what apples look like, what flowers look like, and so forth, and then we can feed this into the model. So as the robot goes up and down the rows now, you'll see the image on the left is the video, and on the right is the robot detecting each individual flower and counting each individual flower as it's going down the road. By the time it gets to the end of the road, it knows all the flowers, it knows the distribution of flowers, it knows where the flowers are per each individual tree. Pieces of information the farmer never could do before. Even when you look at it from a science perspective, being able to repeatedly do something like this 24/7 gives us a large amount of data that we can work with. And just before harvesting season, we did the same thing. So a large collection of data. So the robot going down, you can't see that. You can just see the apples here, but what you can see with the robots is detecting all the individual apples and identifying the information. And again, because now we know each individual tree, we can say there are 5 apples on this one, 10 apples on that one. They're not evenly distributed, or they are evenly distributed. Again, a large amount of information that comes to the grower. So as an example of where that benefits, so you've got this robot going up and down and collecting all this information. Where this becomes a benefit, I should mention, by the time the robot gets to the end of the row, it's already calculated, so it's near real time. Okay, it's not something that we need to then send up to the cloud and then wait a couple of days and then get that information. And so it's a question now of, who's that information relevant to? Is it relevant to the grower, or is it relevant to the robot? Because the robot, once they can, come along and look at pest management, maybe spray an apple, maybe even eventually down the track looking at harvesting, selective harvesting, autonomous harvesting as well. But where it comes a benefit to the grower is an example like this. This is a really good grower, one of the country's best growers. And what you're seeing here is what we've asked the grower is for a collection of rows, can you actually physically count how many apples there are, so we can compare it to our algorithms and make sure that the algorithms are right. Okay, and what you see here is a pretty good correlation in terms of differences between the actual physical count and the algorithm count. But what you also notice is that there's a bit of a drop off over on this side here, okay, in terms of the accuracy comparison. The reason why is it's one of those interesting things about remote sensing in general. When you're going up and down the rows and you're starting to use these different sensors, if you start to get sunlight directly at the sensors, you start to confuse the sensors, whether it's laser or vision or something like that. So it's one of those things that we need to do from a science perspective, easily solved because you just count everything at night and just put your own illuminations and everything's done, so that's not a problem at all. But if you wanted to do 24/7, it's one of those things that we need to target. But the other interesting thing that you see here is that there's a drop-off of yield. So if you look at the apple count, there's a drop-off of yield as you go through. This was not apparent to the grower before this. Okay, so the grower's been operating for 20 years, growing, a very good grower, and has an internal bias in the head. So when we showed him the flower count, he said approximately 80 tonnes